Okay, I want you to think about a compass. Hopefully you've seen one of these before. A compass is a needle floating on a little point. So we have a needle, usually some kind of arrowhead on it, so you can tell which side is which. And what we know is that that needle points north. And people have used this for quite a long time to find their way around. What you might not know is it doesn't actually point north. Like here in California, it points roughly 15 degrees east of north. So you followed it directly along the direction the needle pointed, you wouldn't be going north directly. And the reason is that actually it's following the direction of the magnetic field of the Earth. Okay, we use the symbol B to represent the magnetic field. So just like an electric field, it has a magnitude and a direction, so it's really a vector. Okay. So now, so the nice thing about this situation, this compass, is that it points in the direction of the magnetic field. So we can use a compass to measure the direction of magnetic field. So I want you now to watch the first demo. This is a separate video of some stuff in the lab. So go ahead and watch that now. Really pause this and go watch it now, and then come back. Okay, now assuming that you've watched that, I'll recap a little bit what we saw. So we had a magnet taped down to a piece of paper. And we drew magnetic field lines on the paper. And we found those field lines by using the compass, that we followed the direction the compass wanted to move on the paper, so we could follow the field lines. What we didn't do was follow the field lines that go in other directions. Like there would also be field lines that come up out away from the paper also, and down below into the table. Okay, in fact, it goes out in all directions. All right. And this, because it's complicated, so that makes the diagram almost impossible to understand anymore. So it's nice if we do it in a plane. And so if we imagine looking at it from above, we have this plane here that we're looking in, the outline of the paper. And often we'll just draw something like this. That's just kind of been squeezed down so that we only see this section through all the magnetic field, even though the magnetic field is in other directions also. In that plane of the sheet of paper, that was the direction of the field. We also did this when we did, you mapped the electric potentials and found the electric fields. We were just looking at the field in the plane. Okay, so now we also, in the second demonstration, we didn't look at the field due to a magnet, we looked at the field due to a current. And the current was confined in a loop. So the current went around in a loop. Oh, it's turning out badly. Okay, so we have this loop with the wire wrapped around the loop so that the current went around the loop like this. Okay, and again, we sort of thought about in that plane here, sort of the loop going through it. And we looked at the field, and here the field went around this like this. Okay, we didn't actually do it on this side, but it would follow the same sort of pattern, looping around this way. And also on the top. So we go in, back around like that. And on the bottom. Go around, come out and back around. Okay, so there'd be magnetic field swooshing through that loop pretty much everywhere. Okay, so again, this looked complicated. So let's go ahead and draw the flattened version of it, which is just in this plane here. So we'll take a slice through this plane here that just goes right to this center of the loop there. So here's an important trick. We have to draw the location of that current going down into the paper. Imagine there's like there's the current going down, and then over on this side, this is that one, and this is that one. So when we slice through it, we just see the cross section of that wire. We don't see the whole wire. Okay. Now we have a notation to clarify which one is going down and which is going up. And the trick is, these are the two symbols. So this one signifies a current coming up out of the paper, and this one signifies a current going into the paper. And a good way to remember it is that what we're really thinking about is an arrow. It's a vector. And over on this side, we see the point of the arrow. So you can see the point there. Over on this side, what you see is the feathers of the arrow. So it's going away from you, yeah? So that's a good way to remember which symbol is which. Now that we have it flattened out like that, we can now easily draw the current, the magnetic field. Okay, we didn't draw the other ones, but they kind of go like this. All right, so we'll reuse this idea about this symbol here we use for the current going out of the paper and into the paper. We'll reuse those for other vectors also. One thing I want to point out here, though, is that this pattern here is actually very similar to that one. If we shrunk this one here, we end up with something similar. And in fact, we now know that the magnetic field of a permanent magnet is actually due to currents within the nucleus of each atom. So there's this steady current in each of them, and each of them, because of that current, very much in the pattern like this, each of those atoms has a little bit of magnetic field, and they all add together to make up the magnetic field of the magnet. So in the end, all of these magnetic fields are actually made up by currents. Okay. Now, we have one thing to resolve. The important thing that you should focus on here is this simple picture. There's complications, but this is the part you should remember. That if you have a current going like down into the paper here, it will go clockwise. The magnetic field will go clockwise around it in loops. If you have a current like in this one, with the current coming out of the paper, then the field rotates counterclockwise around it. Now there's a nice rule for how to get this, and that's by using your right hand. So if you imagine holding a wire with a current in it, and you make sure your thumb is going in the direction of the current, then the field will move in the direction of your fingers. They'll wrap around the wire like your fingers wrap around the wire. Okay, so now I want you to watch the second demo. That's going to be showing you about the force on moving charges. So go ahead and stop this now. Go look at the other demonstration and then come back. Let's first deal with the tube with the electron beam in it. And what we saw was, we have to draw in 3D, so I'm set up a coordinate system over here. So we're going to imagine the direction of the electrons was along the y-axis. So the electrons are going this way. Now, I also said that that meant that the current was actually going this way. So we'll draw the current on there too. So that's the direction of Q times V. Just remember that since the electrons are negative, Q times V as a vector is in the opposite direction as the velocity itself. Okay, so now in this situation, we had a magnetic field also, and the magnetic field was going across the table, like level with the table, just like the electrons were going across the table. So there's a horizontal magnetic field, but it was perpendicular and going this way, so away from us. So the opposite of the negative x direction. In that situation, we had a force on the electrons, which was down. So this is just observational. This is how electrons and magnetic fields work. You get a force which is perpendicular to not only the velocity of the electrons, but also to the magnetic field. So if you think of it this way, any two vectors together will form a plane, and the force is perpendicular to the plane of the velocity vector and the magnetic field vector. Okay, so then we did the same experiment again, but this time the magnetic field was coming towards us, and the force was up. All right, and then we moved over to the force on a wire, and we had a similar situation. So the first one was looking at the front now. I'm just going to use, let's go back up here and draw this with our new notation. So this one could be written like this if we did, the current was this way. So we're going to be drawing in the plane created by the current or the velocity and the magnetic field. And the magnetic field was this way. And in that case, the force was down. Okay, so you have to imagine moving up, so you're looking down on the experiment. That wouldn't have been a good place to do the video, because you wouldn't have been able to see the electron deflecting down if you're looking at it from above. Okay, but we can choose to draw it that way. So now the next time we have QV is still this way. Now we switch the direction of the magnetic field. And the force now was upward. Okay, so now let's do the same thing, but for the current. So we actually did, I think there was 4 different situations. We did the current going to the right. We did the current going to the left. We had initially the magnetic field going up. This is not oriented the same way as these diagrams over here. These diagrams are looking down, and these are looking from the front, like we did more or less where the camera was. Okay, and this one, the magnetic field was up. We found in those cases that the force was out, it pushed it towards us, and this one, it pushed it away from us. And then I think we did it again with the magnetic field going down. I turned the magnet upside down. Again with the current going this way and that way. But now the field was down. And the force flipped. Now this looks like it might be confusing, but if you rotated these 3, this is a system like this coordinate system, right? There's an X, Y, and Z. They're all perpendicular to each other. QV, or in this case, this was current. For the direction of the current. If you rotated them, they'd all be the same. So like if you took these and rotated, you could put the current on this axis, the field on the y-axis, and then the force would always be on the z-axis. And this has another right-hand rule that goes with it. Okay, so I call it the right arm rule because it's better to use your whole arm to be safe. So the idea is you put the direction of the current, or Q times the velocity, and you line up your arm so that's the same as the direction of your arm, the current going down your arm towards your hand. And then the nice thing is the reason you use your whole arm is that you have 2 bones in your arm that allows you to rotate your hand. Okay, so you can rotate your hand now. And the thing is, you rotate your hand until your palm has the magnetic field coming out of it. Okay, like you're a superhero or something, you know, and you can shoot beams out of your hand. Okay, so it just comes out of the palm of your hand. So if you do that, orient your arm first, so it's along the current. Rotate your wrist. Don't move your arm anymore. You have to keep your arm still. Just rotate your wrist until the field comes out of your palm. Then your thumb will be pointing in the direction of the force. Okay, whether it's a force on a length of wire or the force on a moving charge. Okay, so that's another right-hand rule. All right, so the nice thing is now we have the direction of the force caused by a magnetic field sorted out, but we don't know the magnitude. And it ends up that the magnetic force is proportional to the magnetic field. It's also proportional to QV or I, depending on whether it's a charge or a current. And for a length of wire, it's proportional to the length of the wire. Now, one thing I mentioned was that in that experiment, when we set it up, I always made sure that the current and the magnetic field were perpendicular to each other. And the thing is that any component of that field that was parallel to the current or the velocity wouldn't have caused any more force. That part doesn't contribute to the force. So we write this all in one equation. We say the force as a vector is a cross product of the velocity in the magnetic field, and then you multiply by the charge. Now, The vector part of this, you guys know how to do with your right hand. So we don't really need that. So if we just look at the magnitude of the force, it's the magnitude of the charge times the magnitude of the velocity times the perpendicular component of the magnetic field. We can do the same thing for the force on a current carrying wires. You take the current, you take the length of the wire as a vector. So the vector is in the direction the current is going, which is also the length. And again, the magnitude can be written as the current times the length times the perpendicular component of the field. So let's draw a little diagram to make sure we get that idea of the perpendicular component. It's sort of like work, remember? We just wanted the parallel component. Now we just want the perpendicular component. So you have, this is Q times V, or L if you want, or I don't know. I tend to think of it in terms of the current, but so you can think of the direction the current is going. Okay, so that's this vector. Then we'll draw our magnetic field in an arbitrary direction. And then we have to break that magnetic field into components. So we put our box here, and we say this is B parallel. Parallel to what? To the current. And this is B perpendicular. Okay, so you need to be able to find the length of this side to calculate the force. Okay, so as long as it's perpendicular, you can use this equation there to get the magnitude of the force. And the direction, in this case, what direction would it be? Check yourself right now. We know this one, we know that one. Use your right arm, line it up with this, rotate your hand until this field is coming out of your palm. And that gives us that the force would be up in the direction of your thumb. Okay, well that's it for now. We'll need to work some problems in the next section.